Hello everyone, we from Group 22 will present the results of our study entitled Comparative Analysis of YOLOv8 and YOLOv11 Accuracy and Static Post Classification, a case study on push-up, sit-up, and squat movement for sports science applications. This study focuses on the detection of push-up, sit-up, and squat movement using two versions of YOLO models. This research addresses the challenge of manual exercise evaluation limitation and leverages the opportunity of automated real-time post-detection. YOLO is selected for its optimal accuracy-speed balance, with YOLOv11 claiming better performance than YOLOv8. The goal is to compare both models' performance in classifying push-up, sit-up, and squat poses for sports science applications.
Hello, I'm Ivana. Next is literature review. YOLO is known as a fast and accurate real-time object classification model. YOLOv8 supports post-estimation, while YOLOv11 brings improvement with a transformer backbone and anchor-free head. In this research, we want to know how accurate two models in classifying pose for sports science. Next part is methodology. In the first part of this methodology, I will explain the sequence of method flow. First, we prepared the dataset we obtained from RoboFlow. Dataset consisting of 3,500 images combining many datasets from various authors relevant to the subject. The images were classified to three categories: push-up totaling 1,573 image, sit-up is 1,000 image, and squat is 1,047 image. Next, we pre-process the data by dividing it into training, validation, and testing sets. Then, we installed YOLOv8 and YOLOv11 using Google Colab and Ultralytics. After that, we load the models and train them separately, one with YOLOv8 and the other one with YOLOv11. Once training was complete, we evaluate both models using metrics such as MAP, and finally we compared the performance of both models based on precision, recall, overall, and accuracy.
Next, moving on to the data preprocessing section, I will explain the process using the following flowchart. First, we start by uploading the dataset to RoboFlow. Then we perform labeling, annotation, and data augmentation. After that, we preprocess the dataset by resizing and normalizing the images. The preprocessed dataset is then exported for custom training. Next, we set up training to use YOLOv8 or YOLOv11. After that, we installed YOLOv11 via Ultralytics. We then fine-tune YOLOv8 or YOLOv11 using the custom dataset. Once fine-tuning is complete, we proceed to custom training. The trained model is then verified. If the evaluation is unsatisfactory, we repeat the training steps. If the evaluation is satisfactory, the process ends. YOLO is known as a fast and accurate real-time object detection model. This is the architecture of YOLOv8 and YOLOv11, which have different functions and architecture. For YOLOv8, the backbone uses CSP darknet, the neck uses FPM plus PANet, and then the head uses anchor-based detection. It supports post estimation and segmentation. And for YOLOv11, the backbone uses transformer-based. It enhances spatial attention. The head uses anchor-free detection. It optimizes for complex and cluttered environment. YOLOv8 supports post-estimation, while YOLOv11 brings improvement with a transformer backbone and anchor-free head. Previous studies have proven that the application of YOLO in sports can aid training and prevent injuries.
The both models were training for 200 epochs on Google Colab with an 800 GPU. We use evaluation metrics such as accuracy, precision, recall, F1 score, and MAP, mean average precision, to assess the performance of each model. As a result, YOLOv8 YOLOv8 excels in precision and minimizes false positive.
YOLOv11 is more stable and consistent in recall and F1 score. Both achieve the same MAP50 value 99.5%, but YOLOv11 is slightly better at MAP50 to 95. The training curve also shows that YOLOv11 has more stable results and better generalization.
The figure shows that YOLOv11 performs better with more stable precision, recall, and MAP values above 0.9. On the other hand, YOLOv8 is lower and less consistent, and overall, YOLOv11 has better training performance and accuracy. These are the object classification results comparing YOLOv8 and YOLOv11.
This study answers three main questions. First, is there a significant difference in accuracy between YOLOv8 and YOLOv11? Second one, how do lighting conditions and camera angles affect performance? And the third, is YOLOv11 better at detecting fast movement? The results support the hypothesis that YOLOv11 is superior overall, especially in complex conditions.
This study produced a comparison of performance of two models, as well as insight for choosing the best model according to needs, evaluation of model performance, impact of dataset size, and recommended model optimization. The research was conducted over 8 weeks, starting from literature study, data collection, labeling, training, and final evaluation.
The conclusion is use YOLOv8 if you want accurate results with minimal errors. Choose YOLOv11 if you need a model that is more stable, consistent, and resistant to environmental variation. The choice of model should be tailored to the needs of the application. Thank you to Google Colab and RoboFlow for their technical support, as well as AI tools such as ChatGPT and DeepL for grammar checking and translation.
Okay, that's the conclude of our presentation, and thank you for attention. See you in the next video. Have a nice day. Bye bye.